Hi there, I'm Stephen T. Lauade, and welcome back to part 6 of my video lecture series introducing the STL, the Standard Template Library. That's what I work on all day. I maintain it along with Dinkomware, the company who originally implemented Visual Studio's STL. And today I'm here to talk to you about algorithms. In earlier parts, we've seen the sequence containers, associative containers, smart pointers. 2 parts covered an extended example in which I used all of the above and some algorithms. Now I think it's time to take a look at the algorithms in more detail because the STL has a lot of them, dozens and dozens, and many different ways to customize them. And it can seem a little intimidating at first because there's just so many options, but it's actually quite simple. The STL usually has an algorithm for whatever you're trying to do, and if not, they can serve as important building blocks, even when you're writing your own algorithms. So the reason why you would want to use an STL algorithm is A, they are often more efficient than what you could write by hand. B, it's simply easier to call an algorithm rather than having to write it out yourself. And also, even if you could write an efficient implementation equivalent in power and correctness to what the STL has already done for you, and even if doing so would be easy for you, it's still a good idea to use an STL algorithm rather than writing out that code by hand, because if you call an algorithm in your source code, it says what it does. If I look at, say, a for loop in my code, I have to look carefully at what it's doing to figure out, oh, this is counting all of the elements of a sequence that satisfy some criterion. Or, oh, this is reversing a sequence in place. Whereas if I see a call to stood count if or stood reverse, then I know exactly what it's doing because the name of the algorithm says what it does. So it's always a good idea to use STL algorithms whenever possible, especially because more and more are added with C++ OX. So let me see. Today I'm going to be showing you the standard in detail. This is actually the C++ OX working paper. It's available freely online. The copy I've got is loading off of our corporate network, but we'll post the URL of the current working paper that anyone can download. It's about 10 megs. Hopefully this font is big enough. So the STL is divided into many, the C++ standard, or working paper, is divided into many clauses. These are the big numbered sections. There's one for the containers, one for the strings. Today we're interested in clause 25, Algorithms Library. If you look at the bookmarks, this PDF has a table of bookmarks, which is exceedingly useful to browse the standard. The other parts of the standard, as I mentioned earlier in this video series, can be somewhat intimidating to read. Certainly some of the stuff in the core language, like overload resolution, is not for the faint of heart. But the standard library tends to be easier to read because it's not so interconnected. And especially if you just want to know the signature of an algorithm, looking at the standardese is actually quite simple. It's sort of my documentation of first resort, just because I know it's all there, and it's actually quite conveniently organized. Of course, you can look at MSDN too, but I tend to just go straight to the standard working paper when I have questions. So the nice thing is that if you simply pop open these sub-bookmarks here, I know the bookmark font may be a little hard to read, but you can follow this along yourself. There are simply each section is numbered 25 to 1, and then it explains the algorithm that it's specifying. So the simplest STL algorithm is for each, and that's down here at 25 to 4. There's other ones that are called non-modifying. We'll see what that means. Then there's a separate section for the mutating ones. And finally, the sorting and related operations, which tend to be the most complicated. We'll look at those as well. So the first division, this is purely informal, but it's useful to sort of keep in your head which algorithms do what, because there's so many, like I said, dozens and dozens. Some algorithms are inherently non-modifying, and that means that if you're throwing this algorithm at a sequence, the algorithm itself won't be mutating any elements in that sequence. Count and find are sort of the simplest examples. Count says, I have a sequence of elements, int strings, as usual. They can be user-defined types, whatever you like. how many of these elements satisfy some criterion. Like how many of these ints are equal to 10, how many of these strings have length over 10, how many of the shared pointers point to something that satisfies so-and-so criterion. That's what count does, and that's simply going to be inspecting the sequence, not modifying it. Same with find. It's going to walk through a sequence from the beginning and say, okay, what's the first element that satisfies so-and-so criterion? Whereas the mutating sequence operations inherently modify what they're looking at. For example, replace. If I say replace if, I'm going to be walking through a sequence, and every element that satisfies some criterion, I'm going to assign something else to it. So take all the ints that are prime and replace them with 0. That's something that I can do with this algorithm. Or transform. This will take one sequence and apply a transformation and write that to another sequence. So most of these algorithms write to an output iterator as part of their operation. And then finally, the sorting and related operations, they either sort sequences or they take sorted sequences as inputs and then do something to it. Binary search is the most obvious example of that. So let's start off simple. For each is sort of the simplest possible STL algorithm. It says for every element in the sequence, do something. Now, for each itself is not inherently modifying, which is why it's under this non-modifying sequence operations header. But the function object that you're applying to the sequence can modify each individual element. In fact, there's a note that mentions this little tidbit in C++ OX. Now, because for each is so simple, you could write just a handwritten iterator loop. Now with auto, it makes it more convenient. For auto I equals v begin and so forth. But if you like using STL algorithms everywhere, even just to blast through a sequence and do something to every element, then for each is your friend. The other STL algorithms are doing more complicated things, and it's always a good idea to use them instead of writing out the loop by hand. With for each, it's sort of debatable whether the algorithm is saving anything. Now with lambdas, though, it can be a good idea to use. So let's look at something a little more complicated. I like looking at algorithms that actually do useful work. Let's look at count. So the first thing you'll notice about STL algorithms is that they're templated on iterator type and often other things like predicates. So as we saw back in part 1, because STL algorithms are templated on iterators, that means that they can work with arbitrary containers of arbitrary things. So if we look at count, it says, okay, count takes an input iterator first, last, and then either a const-ref value or a predicate pred. So I can throw this at a vector of int, a vector of string, a dec of string, a list of shared putter of t, a user-defined sequence, and I can also use this with built-in arrays. Just because I'm using an STL algorithm doesn't mean that I have to be using STL containers. I can use this with stuff like raw pointers and arrays, and it will compile down to code that has absolutely no overhead because everything is a template, everything is a full candidate for inlining, and performance is wonderful, as usual. So let's look at how count works. The first thing you'll notice is that there are two forms of it. There are count and count-if. So what count says is I'm going to be looking for elements that are equal, using operator equal to some value. So I could be looking for all of the strings that are equal to the empty string, all of the integers that are equal to 5, or if I have user-defined type, using its operator equal. Or I could be using count_if, which says, okay, I've got all of these elements, but I'm going to hand you a function object, and that is going to return whether this element is what I call good or bad. Good is true, bad is false. And if this predicate returns true, if the element is good, then I want to count it. So this can be used to do arbitrarily complicated things, like I want to count all of the integers that are prime, all of the strings that are case-insensitively equal to something, or all of the user-defined types that satisfy any criterion. Maybe it's a member function, maybe it's something else that I can determine about that element. So let's look at a little code just to show you how I would call this. Of course, I need to include the algorithm header to access any STL algorithm, except for the ones in numeric. I might mention those. And then, of course, I need a container and IOStream and OStream to print things. And then if I've got a vector of int, V, and then I start pushing back some ints into it. If I had C++ OX initializer lists, I would be able to initialize this vector in a more convenient form. Unfortunately, right now, with VC10, I have no choice but to do repeated pushbacks, or I could create an array and then range initialize from that array. But if I'm going to just type a little code, I may as well do the pushbacks. And then I can do a count. So if I count from VBegin to VEnd, I want to count all of the ones that are equal to 33. And I'm going to want a breakpoint at the end, so I'm just going to put some statement here. We're just going to ignore this. Okay. So if I compile and execute this code, I expect to see 1, because I have one integer that's equal to 33 in this sequence. So let's build it and see what happens. And ta-da! The output is 1. Now, the nice thing is that if this were replaced by a deck or a list or even a map, and I was iterating through this completely different container, the form of the count call does not change. I'm always going to say count, container begin, container end, and then some value, or with COUNTIF some predicate. And I don't need to worry that this algorithm, instead of looking through each element by incrementing a pointer, is instead hopping a doubly linked list by following the links, or by doing a depth first search on a bidirectional map that's actually a balanced binary tree. I don't need to worry about any of that. If I'm viewing this container as a sequence, then I simply pass its begin and end iterators to count. So if you look at this code, this is one of the things I love about the STL. This code has no loops. I have no for, I have no while, I have no control flow whatsoever. This code is straight through, and I'm simply calling this algorithm, and it's outputting a result, and I don't need to worry about what it's doing. I just look at this, this function called count, and it says exactly what it's doing. Now, control flow is inevitably necessary. But it's hard to reason about. And if you worry about bugs, and I constantly worry about writing bugs, because that's what we as programmers spend all of our time fixing and dealing with the fallout of, if you avoid control flow and your code becomes straight through, it's a lot easier to reason about as a human. So I prefer to get the STL to do all of my hard work, and the remaining hard bits, then I can concentrate on that myself. But if the rest of my code is simple, then the parts that are inherently tricky will stand out, and I can focus all of my time and energy on those. So that's count. Now let's look at what would happen if I started using COUNTIF. So let me add another element in here so the sequence becomes a little more interesting. Now suppose I want to count all of the elements that are even. So I can say count underscore if, and I can't type, there we go. And now I'm going to need to provide a function object, a functor, to customize the behavior. So I could provide a handwritten function. Suppose that I provide bool even, and I'm going to take an int n, and I'm going to return whether n mod 2 is I'm even if it's equal to 0. As I recall, I may have written something like this during part 1. This will be a nice refresher, and then we're going to see even more complicated things that I can do with the algorithms. So I can pass this plain old function to COUNTIF, and COUNTIF will start calling my function. So I can pass address even, or thanks to C and C++, the way the core language works, I don't need to take the address of a function in order to pass it around. I can simply mention the function's name. So typically I won't even bother writing the address of there, but if it makes you feel better, you can totally write it. And then if I compile and execute this, I expect to see 2, because there are 2 even integers in my sequence. So let us run. There we go. And what got printed? 2. So I have counted all of the even elements of my sequence. Again, no control flow, and no for, no if. The only if is the underscore if. And what this STL algorithm is doing is it's iterating through my sequence, and for each element, calling my provided function here even, and returning whether this element is even or odd. So that's how I've customized the behavior. I could put a breakpoint in even if I really wanted to see what was going on, and I could watch the STL calling my function. So if I stop and execute this again, the first time even is called, if I look at the local window, this font is small, and I don't believe that I can easily zoom in. I could pop open the magnifier. But what this is saying is that even is first being called with n equal to 11. That's the first element of my sequence. If I continue, the next time it's called is with n equal to 22, and so forth. So the STL is calling my function each time. Now, if you are an old school C programmer, you might be familiar with this concept under the name callback, because you are providing a function pointer to another library, in this case the STL, and it is calling back your code in order to do something. That's a valid way of looking at what the STL does, but I don't like that idea. I prefer to think of it as a function object that I'm providing to the STL in order to customize its behavior. I'm not concerned that the STL is calling back into my code. Yeah, that's what it's doing. I prefer to step back and think of it as, oh, I'm just customizing the behavior of the STL. I don't care that I'm calling it and it's calling my code. I'm simply focusing on the fact that COUNTIF is being given even, and even says what I'm interested in, whether this integer is even or odd. So I could put arbitrary stuff in my function here, and it will work just fine. I could also provide a function object. So this is somewhat confusing. Let's look at this terminology. The STL talks about functors. And functors can be one of several things. They can either be plain old functions, or they can be function objects. And in particular, they can be handwritten, or they can be lambdas. Or they could be constructed from a library. But these are the main ones that you'll see with C++ OX. Now, I should warn you that other authors, if you're reading books, will use different terminology. Often they'll reverse the meaning of function and function object. This is the terminology that I like to use. So let's look at functions first. Everyone knows how plain old functions work. These are non-member functions. You can get function pointers to them. We write them all the time in C++. What a function object is it's a class. Okay, so this is a class. I can't spell. A function object is a class that overrides operator paren. So it's an object of class type that can be called as if it were a function. And unlike built-in functions, function objects can store state as data members. We all know how data members of classes work. So if I have a class that has data members and an operator paren, the function call operator, then it can store state between invocations of its function call operator. So it could be accumulating information, or it could be using that to customize its behavior. This is exceedingly useful. Whereas with built-in functions, they can't maintain state from call to call. Every call of a function is fresh. Of course, you could use global variables or function static local variables, but those are extremely bad. They either leak information or they cause the function to not be reentrant, causing problems with multi-threading. Huge headaches. Never do that unless you have an extremely good reason. Whereas with function objects, because they are properly encapsulated or object-oriented, I don't like that term, they can be used independently. So if I have two function objects with separate state, then it's completely okay to call them independently, perhaps even from different threads, and they're not going to be modifying each other's state. It's completely okay. So I use the term functor as a general term. So if I'm saying functor, then it's either a built-in function or a function object. I don't care which. A functor is simply something that's callable with operator paren syntax. So if I have a functor f, I can say f of x comma y, and this will work whether it's a built-in function or if f happens to be an object of class type that overloads operator paren. I don't care. This is what template will be written to do, and this is how it automatically accepts built-in functions and function objects because the syntax is valid. So with function objects, there's two different types. You can either have a handwritten structor class. If a function object doesn't have any data members, then its function call operator is going to have to be public. You may as well make the whole thing a struct. It's not hiding any secrets. But if it does have data members, you might as well call it class to signify that, okay, this thing is keeping some secrets. So you can either write it by hand, which used to be the usual option, but now with C++ OX, you can write Lambda expressions which implicitly define a function object class and construct an object of that type. It's exceedingly useful. If you look at my Nurikabe example from parts 4 and 5, I use lambdas everywhere. They customize STA algorithms, they customize my own algorithm for valid neighbors, and they are so convenient. We'll see later exactly why they're convenient and efficient. So this is sort of the hierarchy of how functors work. It's simply conceptual hierarchy, no inheritance or nothing, and it is actually pretty easy to use. So I could replace this with a lambda. Let me show you how that works, if you haven't seen lambdas recently. So if I write this, taking, well, let me tabify here, a lambda taking int n and returning, now let's do something slightly different. Let's return whether n is greater than 30. Okay. And that should do it. So I would expect this to return 3 because I have 3 integers that are greater than 30 in the sequence. So compile, execute, and what do I get? 3. Excellent. So what a lambda expression is, it's introduced here by empty square brackets. This is the syntax that the standardization committee chose. And it says, I'm introducing a lambda expression. When the compiler sees this, it knows that a lambda list of arguments and function body is coming afterwards. So you can think of the empty square brackets as a nameless name for a lambda, if you like thinking like that. So this function object is going to take an int n. This will be an element of my sequence, and then return whether n is greater than 30. So the great thing about this lambda expression is that I'm able to write it right next to where it's consumed. When I had to use that function call to even, I had to write it above my main function. That's not convenient, especially if the function that I'm in is long or complicated. Whereas if I put what I'm customizing this algorithm with right inside the call to the algorithm, I can see right there what it's doing. So it improves readability. It's less typing, especially if I had to go write a whole class. And it's also somewhat more efficient than the approaches of either using a built-in function or if I use a library like bind or functional. I suppose I could draw that here. I could either use a library like bind, or if I'm using boost.lambda, that's another example. Or I could use std_memfun. Lambdas are more efficient than built-in functions and significantly more efficient than library approaches, which is why C++ OX added it to the core language. The reason is that this body of a lambda here, because it is a function call operator of a class that the compiler is stamping out for you, it's a candidate for inlining when you're compiling with maximal optimization. So the compiler, when it's generating the code, instantiating the template for COUNTIF, can say, oh, I see that you're calling a function call operator, and I have the source for that. Awesome. Let's inline that so you're not paying any function call overhead. This is exceedingly useful when the body of a lambda is very small, as most lambda bodies are, because you're not paying all of that overhead. With a function pointer, advanced compilers, and in particular VS is capable of this optimization last time I checked, it can inline a call through a function pointer, but not always. If the algorithm is instantiating a lot of helpers, the compiler may not be able to see through all of them and fully inline the call. Whereas with a function call operator of a lambda, it is a candidate for inlining regardless of how complicated the function is. And with a library-only solution, as a library developer, I love libraries. I work on them all day. They're exceedingly powerful, but they're not quite capable of everything. And in particular, when you start to use libraries to stamp out function objects for you, like Boost Lambda does, or like stdbind or stdmemfun, both of which originally came from Boost. Yes, the library is very convenient, but what it's doing is it's generating these function objects and storing what they do, so a function pointer usually, as a data member. And inliners, in particular Visual Studio's inliner, is not willing to see through such stored function pointers. Even if theoretically you could look at the code and say, oh wow, I'm always going to be calling so-and-so function. The inliner can't do that data flow analysis or whatever in order to prove that it can simply substitute the destination into the algorithm. This is a really hard problem. So library-only solutions, they were a good idea for C++ 9803, the old language, but now that we have C++ OX lambdas, we should use them all the time. They are great. You still have to resort to handwritten function objects whenever you want to do anything exceedingly tricky. For example, if you want your functor to be recursive, so its function call operator will call itself repeatedly, please use a handwritten function object. Never think of using a lambda to do that. Horrible idea. Or if the function call operator has to be a template, then you're going to want to use a handwritten function object. You would not be able to use a lambda for that, and you should not try to use something like stdbind because the code that you would end up writing would be very complicated and hard to read. So in conclusion, lambda's awesome, yay. So let's take a look at some more algorithms. We've looked at count extensively. Find just walks through a sequence from the beginning. It does a linear time find. If your sequence is sorted, you can do a binary search, which we'll look at in a bit. Then you can do other things like asking, okay, is this one sequence equal to another sequence? I should probably mention how this works because it has caused confusion in the past. Okay. So the signature of equal looks like this. And first one, last one, first two. Okay. So what this is doing is saying, I've got some sequence that looks like this. We all know about past the end from earlier parts. And then I've got another sequence with first two. And so what std_equal is doing is saying that it's going to compare element by element whether these sequences are identical. So suppose I'm doing this on sequences of int, so maybe a vector int. If I have 11, 22, 33, 44, say this is my whole sequence, and this other sequence also contains 11, 22, 33, and 44. Regardless of whatever this contains, if this is the end of my sequence, then maybe if I redraw this, it'll be more convenient. std_equal here would return true, because as far as it's concerned, this sequence is equal to the beginning of this sequence. So 11, okay, 22, 33, 44, and then it hits the end and says, awesome. You could also compare the lengths by yourself if you wanted to. Now, the important thing here is that the second sequence is represented only by a single iterator. So the second sequence has to be at least as long as the first sequence, if not longer. If it's shorter, that's an error. So if I had something like this, last one, if my first sequence contains 4 elements, but my second sequence only contains 3, this is an error. And the STL can't catch it because it's only taking 3 arguments. So it's going to say, okay, 11 is equal to 11, awesome, 22, 33. Then it's going to advance the iterator into the first sequence up to 44. It'll try to increment this iterator to an element that doesn't exist and then actually try to read it. That's bad. Now, if you're using STL sequences and compiling in debug mode, our iterator debugging checks, which are wonderful, I demoed them in earlier parts, will detect this for you. But you should attempt to avoid writing it yourself, in particular with something like pointers. There's no way to detect that you're incrementing a pointer beyond the bounds. You could argue that, yeah, maybe the STL should be taking pairs of iterators or ranges. That's where C++OX is evolving to. But we have to deal with the STL as it is right now and will be for the next few years. So keep in mind that when you see single iterators by themselves, you do need to provide a guarantee to the STL that there are going to be enough elements for it to consume. This is an even bigger concern when you're working with output iterators. If you're writing to an output iterator, you need to be sure that you have enough elements to scribble into. We have a few warnings that are easily misinterpreted about this, but it's definitely, the burden is on you, the programmer, to be aware that you need to call the STL appropriately. And again, you could customize stood equal with a predicate in order to say, okay, I don't want you to use operator equal equal. I want to ask, okay, if I feed element A from this sequence and element B from this other sequence, what are, I could ask, okay, are they the same parity? Is this one even and this one even, or is this one odd and this one odd, or anything else that I could choose to imagine? At the beginning of this non-modifying sequence operations section here are 3 algorithms that I'm extremely fond of. I use these actually extensively in my NERC hobby program. They are new to C++OX and VC10, so if you have not upgraded, please upgrade. So useful. These are all of, any of, and none of. And I find that I use them all the time because I ask these questions repeatedly. If I've got a sequence, do all of the elements satisfy some criterion? Or does any single element? Or do no elements satisfy this criterion? And the great thing about them is that they're internally storing a local variable bool, walking through the sequence, and then if this element is true or false according to some predicate, then check the current state of the bool and then return. They are, of course, short-circuiting. So if you're asking, okay, are all of these elements prime and it detects a composite number, it'll immediately return. It won't bother to check the rest of the elements. Even though they're relatively simple, they're just so convenient to call. I love them. So yes, that's the non-modifying sequence operations. Let's now look at the mutating sequence operations. These are doing more complicated operations, especially things like random shuffle and so forth. So the simplest one, and conveniently the first one that occurs when the standard specifies, is copy. So what copy does is it copies one range into an output iterator. So its form is copy first, last, result. So it's going to take this range, first, last, and write that into some output iterator. So if my initial sequence, I love these multiples of 11, is a vector of 4 ints, and I'm writing into another sequence. Now this could be anything. This could be another vector, it could be a deck, it could be a list. The elements have to be writable, so it can't be const. It couldn't be a set, because I can't overwrite set elements. But it could be a built-in array or even a raw pointer, as long as I have some length guarantees. Then it's going to simply copy each element until it's run out of elements here. So it's going to take this result iterator, write 11 into it, increment that iterator, write 22, 33, 44, and then it'll hit the end of the source sequence and stop. So like I mentioned, I need enough space at result and beyond in order to be able to store the whole source sequence. If I don't, that's extremely bad. That could even be a security violation, which is why we have some debugging checks for that. But you should definitely avoid getting into such trouble. So the other thing that you can do with copy is have it expand a sequence. So let me show you what this looks like in code, because this is somewhat confusing when you start using the STL. Let me go over here. Okay, so I've got a vector. That's great. And now suppose that I want another container. I'm just going to use vector all the time because it is the container of first resort. It's the container you should be using all the time. Dec and list, the other sequence containers, are occasionally useful, but not nearly as broadly applicable as vector. So I'm just going to use two vectors. So suppose I've got another vector int dest. Okay, this code is wrong. So I am going to show you what the wrong code looks like. If I were to write copy from vBegin all the way to vEnd into dest begin, this is bad. And if I execute this, I will get one of those debugging assertions in debug mode where the STL is being helpful, and it says, whoa, vector iterator plus offset out of range. What that means, we're hopefully going to improve these dialogues at some point. But it's actually telling me what's wrong with my code. It's attempting to increment this dest iterator, dest begin, beyond its bounds, because the sequence is empty. So I mentioned all the way back in part 1, the STL containers are automatically expanding, but you have to ask them to expand. Simply writing to some iterator will not expand a sequence. So if I'm copying 11, 22, 33, and 44 into a sequence that's empty, okay, so this is an empty vector, then if I try to write to that iterator, that'll explode right then and there. The vector doesn't know that it needs to expand. So I would have to here construct dest with 5 elements, because that's the length of the source sequence, and then this is perfectly valid. This will write each element from the source sequence into the dest. Of course, I could have just copy constructed in this particular example, but maybe I'm doing something else. But there is a way to automatically expand a sequence by writing to an iterator, and that's through back inserter. That's in the iterator header. So I've run out of time. So today's homework is to take a look at your own code. I'm assuming that you've written some code that you maintain, or maybe you maintain someone else's code. Take a look and see if there are any cases where you're using handwritten loops that could be using STL algorithms. And remember that you can use STL algorithms on built-in things like arrays and pointers. So take a look and see, by comparing what you're doing with these algorithms that are mentioned in the working paper, see if you could replace any of them with an STL algorithm that's likely to be more efficient, more correct, and certainly easier to read. So that's that. See you next time.